So here we are on question 9. Now, question 9, I think, is a very interesting question. It's about drinking tea, which is one of my favorite pastimes. So here is part A and the introduction to it, the context. Hot tea is poured into a cup. The temperature of tea is modeled by this function. So CT is equal to 25 plus 70 times 1.5 to the power of minus 0.4 T, where C is the temperature of the tea in degrees Celsius, and T, the letter, is minutes after it is poured. What is the temperature of the tea 4 minutes after it's been poured? Give your answer correct to the nearest degree. So it's obviously a very straightforward question to begin with. You're just subbing in 4 for the letter T, and you get your answer, and correct to the nearest degree is 62 degrees Celsius. Okay, so you do obviously need to round it correctly, and you want to put in your unit just to make it clear that you know what's happening. So 5 marks for that, an easy 5 marks. Now, at what rate is the tea cooling 4 minutes after it's been poured? So obviously we've just gotten the temperature at 4 minutes. So what is the rate? And as soon as you see the word rate, you're thinking rate of change, you're thinking differentiation. So in this case, it's a straightforward, just differentiate the function, give your answer in degrees per minute correct to 1 decimal place. So we have to look at obviously where the variable is. And what we're going to have is we're going to say the rate of cooling. So the first derivative, C dash T. So what it is we're coming from the 25 is going to disappear because it's a constant. And then we have 70, which is just the coefficient, times 1.5 to the power minus 0.4 T. So we know, just to go back on the basics, if y was equal to e to the power of x, then dy dx would be e to the power of x. If y was equal to e to the power of ax, well, then dy dx will be equal to a times e to the power of ax, and the a coming here because of chain rule. If y was equal to a to the power of x, that implies dy dx would be equal to a to the power of x times ln of a. So that's on page 21 of your table books. And if y is equal to a to the power of bx, well, that implies dy dx is equal to a to the power of bx times the ln of a, but also times b, but where that b is not part of the ln of a. And the b is there because it is the derivative of the coefficient of the power. So the derivative of bx would be b. So that's chain rule there. Now, in this case, so when we're focusing on this part up here, you get 70 times 1.5 to the power of minus 0.4 T, but it is times the ln, the natural log of the base, ln of 1.5, but you're also multiplying by the minus 0.4 because it is the derivative of the power, the derivative of minus 0.4 T. So there's a good bit going on there. You simplify it all down, right? And just to say that this part is all one kind of aspect of it. Okay, that's all one aspect. Sorry, see there now, I actually highlighted or kind of took the wrong part of it. So if I just clear all this here away, just to be certain, like, the 1.5 to the power of minus 0.4 T, that's that part there, okay? So that is going to be dealt with in a moment when we put in the 4 for T. Where did everything else come from? Well, the 70 times the minus 0.4, that's your minus 28. And then your ln of 1.5, well, that's the last part there. And remember, that's just a constant. So when we put in 4, then for T, well, in that case, then we're going to now be able to type that all into the calculator and get minus 5.9. We want to correct to 1 decimal place, so it is minus 5.9. The T is cooling at 5.9 degrees per minute. So 10 marks for that. There is quite a little bit of work in that. There's a lot of places where people could go wrong. I could imagine people going wrong with the ln 1.5, or even if they had that, they might forget the minus 0.4. Okay, so on to part 3. How long after the tea is poured will it take for its temperature to reach 55 degrees Celsius? So that's not differentiation. That's just your original function equals 55. So because this is your function for temperature, when is the temperature going to be 55? You take the 25 here from your 55. So what's that going to give you? 30. You're going to divide that by 70. Why 70? Because you're dividing across by the coefficient on the 1.5. It can only work to go to um, into logs. And actually, I gave you the wrong page there a moment ago. It's page 21 is your rules for logs. But of course, we were looking at page 25 for your rules for differentiation earlier. So page 21, in this case, we're going to be using our key rule of logs, where we're going from indices to logs. So this rule over here, a to the power of x equals y implies the log of y to the base a equals x. So what that means is, at this case, when we're going from indices, in this case, to logs, right? Well, actually, you can do it in a couple of different ways. Actually, I'll do it in my key rule of logs way first, right? So you can do this. So I could simplify that down, right? And I'm going to say I introduce logs. The base number will remain the base. What was my answer, which is the 3/7, would become my power. And what was my power would become my answer. So basically, these two pieces here switch. The base number remains the base. I can type what's here. I'd be able to type that into the calculator and get an answer. And of course, I know I'm going to have to divide it by minus 0.4 to get t on its own to solve the equation. Now, another way of doing it is to take the logs of both sides. In this case, we're going to take ln of both sides. So this is what I'm going to do now here down below. So I could take ln of both sides. So remember, that's log to the base e. So I'll just write it as log to the base e for a moment. So log to the base e. And then we'll remember that if you have the third rule of logarithms, which is the power to the front law, if you have log x to the base, x to the power of q to the base a, you can bring the q to the front. So I'm going to do that here with the minus 0.4t. And so just to describe what I'll have, then I'll have minus 0.4t times log 1.5 to the base e. Okay. And that would be equal to the log of 3 to the base e minus the log of 7 to the base e. Why is that? Because I'll be using the division law here, the second law of logarithms. So log x over y to the base a is log x to the base a minus log y to the base a. So same sort of idea there. And when I simplify that down, I'm going to get this line. Okay, so I'm just kind of rewriting it. I'm going to rewrite it as ln rather than log to the base e, but it's the same thing. And of course, they're all just numbers, right? So to get t on its own, I can divide both sides by my constant. And my constants are minus 0.4 times the ln of 1.5. And I'll be doing the same over here. I'll be dividing it by minus 0.4 times the ln of 1.5. And I can put all that into the calculator. And when I put all that into the calculator, I'm going to get an answer, which is 5.224234. And that would be the exact same thing as if I put all this into the calculator up here. I'll get the exact same number. And correct to one decimal place is 5.2 minutes. So after 5.2 minutes, the temperature of the tea would be down there at 55 degrees. Okay, so that's part A dealt with. No, so part B is different from part A, but the context is the same. It's still about drinking tea. The average cup of tea contains 20 milligrams of a substance called caffeine, which enters the bloodstream. There it is gradually broken down and absorbed according to a differential equation. Ct is equal to A times e to the power minus 0.3 t, where C is the amount of caffeine in milligrams in the bloodstream at a time t, T is the time in hours this time around, so you just got to be careful. It was minutes earlier after each drink. And A is the initial amount of caffeine consumed. And again, like my finding is, my understanding and my experience tells me that students, as they go through a question, they can get a bit confused. Like this part of the question is completely separate from the first part. So if you just started at this part of the question, you'd be able to do it. But sometimes people get confused between the part A and the part B, we'll say. If a person drinks 1 cup of tea, how much caffeine will they have in their bloodstream after 2 hours? Give your answer correct to the nearest milligram. So there's a very important clue up here that the average cup of tea contains 20 milligrams of a substance. So because of that, we can say that we know our function. And this is what I always say to students, this same trick takes place with this type of function all the time. So when it says the word initial means at the start, at the beginning, or when t is equal to 0. So when time t is equal to 0, the amount of caffeine is 20. Minus 0.3 times 0 is 0. E to the power of 0 is 1, because anything raised to the power of 0 is equal to 1. So that means A is equal to 20. Now, some of you who would know that trick and have seen it a few times, you'd be able to just write down that A equals 20 from the very start, because it tells us the initial, A is the initial amount, and it tells us that up there. So then it says, okay, well, how much caffeine will there be after 2 hours? Then you're just putting in 2 for T, simplifying it down, and you get, correct to the nearest milligram, 11 milligrams of T. Okay. So after 11 milligrams of caffeine. So after 2 hours, you have 11 milligrams of caffeine still in your system. And 10 marks for that. So as I said, that 10 marks could have been gotten without ever doing any of the earlier parts. And that's just something that people need to hear a lot of times. Some people will be looking for the exit door at this stage once they see this question. The next part, it says, one evening, Geraldine decides to stay awake all night to read an entire novel. Maybe some of you could have been trying to do that when you were studying for this exam, which will take her 10 hours to read. So 10 hours is the important part. The novel bit isn't. To do this, she uses the following strategy. She starts the novel after she has drank 1 cup of tea. So again, starting it is that initial time. And then she waits until she begins to feel drowsy, which occurs after the caffeine level in her bloodstream falls to 12 milligrams. Now, have we seen that 12 milligrams before? Not quite. It was after 2 hours, she had 11 milligrams. So it'll be slightly less than 2 hours. She then drinks another cup of tea. She then waits to feel drowsy again when her caffeine level falls to 12. She drinks another cup of tea, and so on. How many cups of tea will Geraldine drink during the night? Okay, well, you might have to think about this for a little bit, okay? So that's, you might have to look back and read through it a bit, you know what I mean, to remind yourself of the question. But the second cup is going to be drank when our caffeine levels falls to 12. Okay. So again, this is very similar to the question we did earlier. Our answer is 12. We must find, that's like our output of the function, and we must find our input, which is T. You're going to divide across by 20. So you could simplify that down if you want to 3/5, okay, 0.6. And in fact, a lot of students, that's just a small little tip, a lot of students do find it easier to deal with that in decimals. And again, I would use my key rule of logs here, where I'd say, okay, remember, a to the power of b is equal to c. That implies the log of c to the base a equals b. So in this case, I could say, well, I introduce logs. The base remains the base. What was my answer? The 0.6 would become my power. And what was my power will become my answer. And then I just divide both sides by the minus 0.3. And I get my solution, which will be the letter T. So in this case, I could do it differently. I could take the log to the base e of both sides, remember, which is ln. So log to the base e, log to the base e, And so that's what it'll look like. I can then use my power to the front law. So minus 0.3 T times the ln of E. And I hope you realize the ln of E would just be equal to 1 because it's log E to the base E. E to what power gives E? The answer is 1. Is equal to ln of 0.612 over 20. So I divide across by the minus 0.3. And remember, that's going to give me the exact same as this one over here. And I get my answer of 1.7028. And that is how long it takes to go from 20 milligrams down to 12. Now, the next thing is, though, we have to remember she doesn't go back to just 20. She goes to 32 milligrams because the cup of tea gives her another 20. So now she's up to 32. So in this case, we'll say A in relation to the function now has changed to 32 because the initial amount after drinking cup number 2 is she's now up to 32 milligrams. So again, you divide across by the 32. You're going to do the exact same idea here. You're going to introduce logs. You're going to do this exact same work as we did earlier. You're going to end up dividing across by the minus 0.3. So that is 3.2694. So what that number represents is after she's drank cup 2, how long does it take until she drinks cup 3? Okay, so that's 3.2694 hours. Because that's how long it takes to go from 32 milligrams down to 12. So then you'd say, well, okay, will she get to drink the third one? So this is the first cup, the first cup to the second cup. Well, she drinks the first cup. It's 1.7 hours later, she drinks the second. Then 3.2694, she drinks the third. So she'll have drank the third one. But now what are we up to? I'm looking at the numbers here. 2, 5, it's like 8.2, 8.3, something like that. 8.3 is less than 10. Okay. But is she going to drink the fourth cup of tea? Geraldine drinks 4 cups of tea. Let me just have one look at this. Because we have to look at the question again, just to be sure on this. How many cups of tea will she drink? So she drinks 1. Then after 1.728 hours, she drinks the second one. So that's my second cup. She drinks a third cup, and she does drink the fourth cup. She drinks the fourth cup of tea, okay? But she won't get to drink a 5th cup. And then I think there's a last part in it. What will her caffeine level be when she finishes the novel? So there's a little bit of work here, a little bit of thinking about this one. So she drinks her first cup. 1.7 hours later, she drinks the second. 3.2694 hours later, she drinks the third. 3.2694 hours after that, she drinks another. And so between the time she drinks her last cup of tea, so her fourth, and the time she finishes is 1.7584 hours. Okay. So that's how long the caffeine is dropping for. She, at the start of this time period, she would have 32 milligrams because after drinking her fourth cup, she'd be topped up to 32 milligrams. The time that she is reading the novel and running down her caffeine is 1.7584. Okay. We put all that into the calculator and we get an answer of 18.8821 milligrams. So the caffeine remaining will be 18.9 milligrams correct to 1 decimal place, isn't it? Correct to 1 decimal place. What would our caffeine levels be? And so we're saying 18.9 milligrams of caffeine will be remaining in her bloodstream. So that is the end of that question. And we're going on now to our final question, which is an area and volume one. But I hope you enjoy that level of that question there. You will remember now next time you're studying that the caffeine, if you're drinking tea or coffee or Red Bull or anything like that, that it decreases in the same way. Doesn't mention anything here about how much is too much, but there's definitely too much out there for study purposes. Okay, let's have a look at question 10.